So, I have two sets of slides about logic, and I don't think I will manage to finish them before lunch. So we will look at half of them now, and then we will come back and look at the second half after lunch. Okay. This logic is called Hennessy-Milner logic. It's due to Hennessy and Milner. Matthew Hennessy is still alive, very interesting person to talk to. Robert Milner unfortunately passed away. And it's a special type of modal logic, and it's also a special type of temporal logic. And getting back to someone who asked whether there is any other fundamental model, I think he left. So typically if you go to the US, the type of temporal logic that people talk about are mostly state-based temporal logic, so LTL, CTL, CTL stuff. In Europe, or at least for a major part of Europe, this type of action-based model logic is more prevalent. But they can be translated in one, I mean, there are standard translations from a state-based to action-based and vice versa. So there is no fundamental difference between using Hennessy-Milner logic or using some type of branching temporal logic in the state-based world. The good thing here is that we use modal mu calculus, which is much more expressive than any other logic that you've seen. So it's much more expressive than LTL, CTL, CTL star. And it allows you to specify very complex combinations of path and state or action formulating very strange ways of recursive specification. But we'll get back to that. I won't talk about that right now. I will keep it simple. And I need my mouse somewhere, which I left. Okay. Right. So remember we talked about system models. So that for that we use MCO2. We translate them into a semantic model. Then we have label transition systems. We'll look at behavioral equivalences to compare them. Now what we'll do, we'll look at modal formulae as a way of formalizing your requirements, and we'll specify how you could check these formulae on your semantic model. Okay, so that's the purpose of this lecture. So previously we could verify systems using behavioral equivalences. You could have a high-level specification, you could have a low-level implementation, you could check whether they are branching by similar or not. That's one possible verification method, which you could use also for your case. The drawback, well, this is not really a big drawback, so that this could be used. I'm not saying this is not a viable path. But you do need a complete specification of some sort of both the high-level and the low-level system. And then not always you feel like specifying things in so much detail. Sometimes you want to also, you only want to specify just one scenario, right? And yeah, it's rather difficult to give concise specification of complete systems. And then that begs the question why your specification is correct if it becomes so complex. Right? So what you would like to do, you would like to have only partial specification of the system. And for that, logic might be the way to go. So logic might give you more concise specification of one aspect of your system, correct? It's a full specification. Right? So what we do, we specify our requirements, our correctness properties outside the behavioral model and the logical formula, and then we verify them on the behavioral specification. So basically, we look at the input-output behavior of a system, we look at it as a black box, and we try to relate these different events in time. That's why we use temporal logic, because the relative order of these events are very important, and they typically characterize what the correct behavior is. Right? Temporal logic goes back to old Greece, I think. So even people like Plato and old Greek philosophers talked about temporal logic. But it has come to computer science maybe 50 years ago, 40, 50 years ago, by people like Noemi, Mana. And Hennessy-Milner logic is just one type of temporal logic that we use in this. So we specify the properties in temporal logic, and then we verify correctness by specifying the semantics of our temporal logic on a label transition system, basically. So a typical system that I will use is about a scientist. a scientist can interact with the environment by drinking coffee, by putting a coin in the coffee machine, and by producing publication. That's typically what a scientist does, so nothing more than that. They also may do some unobservable actions every now and then. The property, one property that you would want to specify is that the scientist is not willing to drink coffee now. He or she has just drank a cup of coffee, so she doesn't want any more coffee. Or the scientist is willing to drink both coffee and tea now. Look, these two properties only talk about the behavior right now, right? So we talk about the current state of the system. There is nothing temporal about it. Yes. But another property that does talk about time is that the scientist will always produce a publication immediately after drinking 2 coffees in a row. Right? So this is not talking about the current state. It talks about the state in which you have already drunk 2 coffees, and then afterwards immediately you should produce a publication, right? So it talks about sometime in the future. And for that we use this syntax that I will introduce right now. So the first pieces of syntax you know from propositional logic, in case you have seen it before. In case you have not seen it, which is unlikely, I will explain. So true is the basic anthem. It says, well, it's true. You don't need to prove anything. It trivially holds. False never holds, right? In no state of the system false holds, otherwise you have a contradiction. Not fine only holds if phi does not hold that in the current state. That's also what you do expect. Phi and psi hold if both phi hold and psi hold in the current state. Phi or psi hold if either of the two hold or both. And phi implies psi hold if whenever phi holds, psi also holds, basically, right? Or otherwise said, if not phi or psi. And now this is new. This you may not have seen before if you haven't seen the NSMR logic. This one says, you read this as diamond A phi. This one says you can do an A action. So it is possible to do an A action right now from the current state. And afterwards, in the target state, after doing this A, formula phi holds. So you can take an A step, and in the target state, phi should hold. Okay. Is this clear? I guess most of you have seen this also. This one reads box A phi, and box A phi means if you can do an A, no matter how you do that A, afterwards phi will hold. Okay. If you can do an A, no matter which A you take, then phi holds. However, this formula also trivially holds if you cannot do an A. Right, so it says if you can do an A, no matter how you do it, phi will hold. But if you cannot do an A, then that's also fine. Yeah, so after all A action, phi should hold. But if there is no A action, there is nothing to check. That trivially holds. Right? Just to test your, what does this formula say? Sometimes I write true, sometimes I write top. They mean the same thing. What does this formula say? Anyone here? It's true. Let's say for someone else. Anyone?
It's not deadlock.
It's not deadlock, no.
It means A plus. A plus.
No, it's not A plus either. So let's look at the informal specification. It says if all successors reached by performing an A action satisfy phi, right? There are 2 possible cases. Either in the current state you cannot do an A, right? So you can do things like B, C, but no A. Then this formula is true, right? In such a system in which you cannot do an A, this formula always holds. Right? Or you can do an A, or maybe multiple A's, and then true should hold, but true holds everywhere. So no matter whether you can or cannot do an A, this formula always holds. So this is logically equivalent to true. Never combine a box with a true. Likewise, but now I've given away the hint. What does this formula say? Diamond A false? You know, of course. Anyone in tears? you knew. So this is trivially false because either you cannot do an A, but the informal description says you should be able to do at least one A after this by hole. So if you cannot do an A, for example, you can only do B and C, then this formula is false, right? Or you can do an A, but then you're doomed because you have to satisfy false. False can never be satisfied. So this is logically equivalent to false. Regardless of whether you can do an A or not, this formula is always false. Right? Because if you cannot do an A, then you violate the property that you should be able to do at least one A. If you can do an A, but then you should satisfy false. That's impossible. So never combine diamond with false. That's always false. Right. So how do you specify that the scientist is not willing to drink coffee now? And please do not just raise your hand so that we can have several answers. There are multiple answers to this question. Multiple correct answers to this question. So there are correct answers and alternative correct answers. Right? As the Trump administration. So how do you specify this? Any volunteers? Do you want to volunteer? No?
Yes.
Yes?
Willing means it's can. You may
Yeah, willing means can. Yes.
It's not diamond drink coffee. True.
Okay, so we already have made some progress because we are not combining diamond with false. That we should never do, right? That we learned from the previous board. And this is saying, what does this one say? It says you can do a coffee right now, and then you satisfy true. Right? So it says it is possible to do some coffee transition. Right? So diamond coffee true says it's possible to do some coffee transition. Right? Not diamond coffee true says it's not possible to do any coffee transition. Right? So that's the correct answer. Any other suggestion? One more suggestion, please. Yes?
Box coffee false.
Perfect. Box, coffee, false. This says, if you can do a coffee, then you should satisfy false. You can never satisfy false, so you better not do a coffee right. If you do a coffee, then you should satisfy false. You better not do a coffee right now because you can never satisfy. And there is this duality between box and diamond. So by pushing negation, you always turn a box into diamond and vice versa. So one of them is essential, and the other one can be derived from the other, like conjunction and disjunction. They are dual to each other using De Morgan's law. Here there is a similar De Morgan law between box and diamond. You need one of them, and then you can derive the other. Right? Okay, so this is the answer for this one, right? Or the other one. Both are correct. The scientist is willing to drink both coffee and tea right now. How do we specify that? Some other person who hasn't? Would you like to say something? Would you like to say something?
Box coffee and tea.
Okay, so I will write it down and then we'll correct it later. Okay. Box coffee and
tea.
inside the box. Syntax error.
Box coffee.
Shall I show you the syntax? This is the syntax. So you are only allowed to use this syntax. Inside the box you can use the same language for the time being. I want to say that you are willing to drink both coffee and tea.
Diamond coffee.
Diamond coffee, yeah. Okay, very good. Diamond coffee, true. Right.
And diamond tea.
Perfect. That's very good. So this is saying you can do a coffee action right now, and then you should satisfy true, which is always satisfied. And you can do a tea action right now, and then you satisfy true, but that's also trivially satisfied. So you can do a coffee, at least one, maybe more, and you can do a tea right now. And that was exactly what you wrote on we wrote down in plain English, right? The scientist is willing to drink both coffee and tea, right? Right? Coffee, sugar, and tea. Very good. So, a typical formula that you use during your specifications. The process is deadlocked right now, and assume that you have only two actions. Some other volunteer, how do you write? If you have only actions A and B, how do you write that the process is deadlocked right now? Do you want to say something? No? What does deadlock mean? It means that you cannot do any action, right? Here we have only A and B. How can we say that you can neither do an A nor a B? Would you like to say something? Not what? No, not. Shall I go back to the syntax? Do you want to do the syntax? So I want to say that you can neither do an A nor a B. You are deadlocked. Well, syntax error, because I cannot use action here. I can only use action inside diamond and box. So do you want diamond A or box A? Otherwise I cannot write A.
Not diamond A.
Okay, and then I need some other formula after diamond?
False.
True.
And not diamond.
Perfect. It's basically the same thing as we specified here, right? Here, we said the scientist is not willing to drink coffee right now, not diamond coffee, true. Here we are saying you cannot do an A and you cannot do a B. Basically, you're deadlocked. Yeah? Good. Very good. Or, dual to that, you could write box A false and box B false. Just like this, right there. Oops. The process can do something, so it's not deadlocked. Do you want to say? You passed last time. Do you want to say that the process can do something, some action?
Diamond A.
Uh-huh. Diamond A what? True, because you can never write diamond A false, that's false, always. Diamond A true, or? Right. You want to say the same, or you had a different? Yeah, good. Very good. So I think we got a grip of how this works. A must happen next. That's an interesting one. A must happen next. Anyone in here? Take 10 seconds, think about it, and then say something. A must happen next. What did you say? Oh, sure. A must happen next. Let's say, let's see, what do you say?
Box A. Then
What box A? That's syntax error, right? So box A should be followed by some formula, and implies it's not a formula, right? So I take this back. What did you say?
What's the box A?
Not box
A.
A. Oh, never combine box with true. That doesn't go.
Diamond A true.
Okay, but now you know everything. Diamond A true, right?
And not diamond B true.
Perfect. So this is saying you can do an A, right? You can do at least one A, and you cannot do anything else. In this case, there is only B to do, right? So you cannot do a B, and you can do an A, so you are forced to do an A next. You can do an A, and you cannot do anything else. In particular, you cannot deadlock because you should be able to do an A here. I wrote it slightly differently, so instead of this, I wrote box B false. And you will see later on, maybe after lunch, that there is a syntactic sugar, so just a simple extension of the language, by which you can put sets of actions. Sets of actions in dynamic box. I will define that in terms of dynamic box. And then it becomes much simpler. So if you don't know what your sets of actions are, you can say act, for example. And box act false means that you cannot do anything. You basically get it. I'll show that next. And then you can use regular expressions and all sorts of different things. Right. I have an algorithm for bump checking here, but I won't present it because I think you have an idea how it works, right? So you basically start with the subformula, you label all the states in the subformula, and then you grow until you reach the original formula. It's not the algorithm that is using the tool, it's a different type of algorithm that goes through the linear processes into a Boolean equation system. But this is just to give you an idea how you could verify formula on a label parameter system. I think I will skip that. I'll just give you one example to show how it works. So suppose I want to verify diamond A, diamond B true. What does it say? Diamond A, diamond B true? Your formula?
A action and then B action.
So it's possible to do an A followed by B, right? A, B trace is possible. This system features a trace labeled A, B. If you want to verify that, I first start with the smallest subformula here. In this case, I have true. So I label all the states that satisfy true. All of them do satisfy true. Right? Then I grow my formula to the next smallest subformula. In this case, diamond B true. Which states satisfy diamond B true? Which states satisfy diamond B true? Yes. Right, S2 is the only state that satisfies diamond B true. The rest cannot do a B, right? So S2 is the only state that satisfies diamond B true. And then the next subformula is diamond A, diamond B true. Now I know which state satisfies diamond B true, so I only need to find those states that have at least one A transition to this particular state. And what is that? It's only S nodes, right? S0. And then I'm done. I've labeled all the states with that satisfy the original formula. I look up and check whether the initial state is among them. In this case, this is among those. This is the only state that satisfies the formula, and then thereby I conclude that the label transition system satisfies this formula. Okay. I guess this is a good point to stop. You will have access to slides, so you can look at the other cases, but these are very similar, and there's nothing deep about it. I think you have an idea how this should work. Right. Let's see one more example, and then we go for lunch. Okay. So what if I want to specify that the scientist will produce publication immediately after having drawn two coffees. How do we specify that? Spend a few moments, maybe 10, 20 seconds, write it down. Any volunteers? Anyone who didn't say anything today? Did you say anything before. Would you like to give it a try?
Not diamond coffee. Again, diamond coffee.
Okay.
Diamond. Excuse me, not a diamond pop.
Another knot? Here?
Yes.
Okay.
No, after that.
After that, okay.
Yes.
Not diamond.
Pop. Pop. Publication.
Okay. Not diamond publication.
True.
True. Okay, let's first understand what this one is saying. So it says it's not possible that you may do 2 coffees and you're not able to produce a publication, right? It's not possible that you may drink 2 coffees, so there is no such trace in which you first drink 2 coffees and basically waste them, but not by not being able to produce a publication, right? That's it's not possible to drink 2 coffees and afterwards not be able to produce it. But, okay, look at this one. Assume I have another action. I don't know, okay. How about, so, take an infinite transition system in which you may produce a publication after each coffee, but you may also avoid it by drinking another coffee. So there we have a lousy scientist that can produce a publication after drinking each 2 coffees, right? But it can also avoid it by drinking yet another coffee, and then avoid it indefinitely in the future. Does this satisfy this formula or not?
Sorry, I mean anything other than publication.
Let's first answer the question. Does this transition system satisfy this formula? It does. Everyone agrees with that? So the scientists can avoid producing a publication by drinking yet another coffee. Right? So this is not yet good enough. It's a very good attempt. It's very close, but it's not yet good enough. What's your suggestion?
I mean with last formula I want to try with any action other than publication. Not
So in this,
bar.
could you help me with that? Any other action is only coffee. What do you want me to write? So we only have pop and coffee, nothing else. What do you want me to put here?
Coffee.
No, you don't want coffee here.
You should eliminate the not sign.
No, but this is not good because a very good scientist may produce let me see. So it's not possible that you drink 2 coffees and then you can drink another one. It's not possible that you drink 2 coffees. Okay, so look at this one. This one satisfies your formula.
And we should write this part again and we should write part 2.
What do you want me to write? It's getting close. Don't feel shy. What?
We should write the formula from the first.
Oh, once again. Okay, I will do that. I think it's a waste to write it once again, but I will do it.
And
You don't need to write it once again.
we don't need to write not sign.
And then
But
diamond pop through.
and should eliminate the not sign from.
That's not good either because I can add this here. this transition system satisfies this formula because, first of all, in all paths, it's not possible to drink 3 coffees in a row, so it satisfies this part. And also, in some paths, it can produce a coffee after a cough, but you can avoid it by taking this other path. So let's take it step by step. I think it's very close, so because we want to go to lunch, I will try to solve it together with you. First of all, we have to produce a publication at a particular state after having drunk 2 coffee. How do we specify that we have to produce a publication? How do we write it down? That we must produce a publication right now. How do we write it down?
And box
coffee. Perfect. So this is saying you have to produce a publication. Diamond pop true, you can produce a publication and you cannot do anything else. Right? This formula should be satisfied after having drunk 2 coffees in a row. No matter how you drink 2 coffees in a row, this formula should be satisfied. How do we write that down? No, not diamond, because diamond is just saying one possible path, right? Box coffee. Box coffee. If I want to follow the path you are looking at, just to take diamond with negation, that's also fine, right? So I think your answer is also correct if you just put this one there and you get what you want. So no matter how you drink 2 coffees in a row, and if you run out of coffee, then you have no obligation to sign this, right? So coffee should always be ready. If you drink 2 coffees in a row, then afterwards you should produce publication. Right? So on that note, I think we can close this lecture, and then when we come back, we will talk about some more complex types of logics that build upon Hennessy logic. Okay. So we will reconvene at 1:30. We may spend an hour, maybe an hour and a quarter, to discuss a little bit of logic and then the exercise, because the exercise is very important. We really want to get something done. And then we will go for a social event. We will go to one of the palaces in the north. I think the Concurrent palace we are going. There are taxis booked, so we will go together, and then we have enough time to discuss any topic of choice there. We will go around in the palace, and then we will sit somewhere to drink some tea or something. And if you have any questions, we could also do it during the social event. Okay? So we now go for lunch. We come back 1:30 to continue on this topic and then on the exercise. Around 2:30, maybe 2:45, we will leave to the social event. Any questions? If not, see you at 1:30 sharp, because we're really pressed in time. You have a question? There are no other questions right now, so we can go to lunch, and lunch is as yesterday at -1. Talked about Hennessy-Miller logic. We could also take it in Farsi, but I think Kian Friso is coming later on, so let's do it in English. We talked about Hennessy-Miller logic in the past lecture. Now we are going to extend it with some new features. Still, we are talking about this bit, right? So we are talking about a mode of specification which can be used to formalize our requirements, and then we have a way of verifying those on the semantic domain, namely labeled transition systems. So we discussed a little bit in the past lecture how we could specify such properties, but there are some intrinsic problems with what we discussed in the last lecture. Namely, for example, if you want to specify that the system is deadlocked, we need to know the set of actions and we need to mention them one by one. So if you remember, we had this one. This one was a specification of absence of deadlock. Either you can do an A or you can do a B, because you only had these 2 actions, right? If you had a third action C, then you had to add another disjunct, or you can do a C, and then it would go on forever, right? And potentially when you have data, you have infinitely many actions, so you cannot specify such things as finite formulae. So that's one handicap of what we discussed in the past lecture. Your specification is very much dependent on the set of actions that you're considering. That's one handicap. The second problem is that you cannot specify things that require going over an unbounded number of actions. So if you want to specify that something always holds, regardless of the number of steps that you take, you cannot specify it using a finite formula in Hennessy-Miller logic, because you don't know how deep you should go into your transition system, right? You can say this holds after each A and each B and each C. It holds after each sequence of A's followed by B's, A's followed by C's, B's followed, all sorts of combination, and it should go unboundedly deep into your transition system, which is not possible. So what we will do in this lecture is to remove these problems and extend the Hennessy-Miller logic with constructs that allow us to specify this. So for example, if you want to specify that something invariably holds, something that you would specify in LTL, for example, as AG something, right? That would correspond to phi holds right now. And phi holds after all actions. Well, this represents all actions somehow. And it holds after every 2 actions in a row, every 3 actions in a row, etc. And this will be unboundedly many. There will be unbounded many. Likewise, if you want to specify that something will possibly hold in the future, you should say phi holds now, or it will hold. It's possible to do it true after which phi holds, or you can do 2 actions after which phi holds, etc., etc., which is an infinite formula. So the first extension of Hennessy-Miller logic that we use here allows for specifying sets of actions inside diamond and box. Okay, so before you could specify only diamond A or box A. Here you can specify diamond with a set of actions. Okay, and this is a syntactic shorthand for diamond A1, diamond A2, or diamond A2, or diamond A3, up to diamond AN, where A1 to AN is your set of actions. Okay, so it says either you can do an A1 after which phi holds, or you can do an A2, etc., or you can do an AN, right? So it basically says you can take one of these actions in this set, and afterwards a phi should hold. Is this clear? So how would I specify, if my set of actions is act, how would I specify the absence of deadlock now? At the current moment, how do I specify that the system does not deadlock? You're all sleepy. Okay, I heard the wrong answer. let's write it down. Right. So never combine box with true, right? Diamond act true, right? And it says you can do something, and afterwards true will hold. True holds everywhere, so the only requirement is to be able to do something, right? Oh, yeah, and by the way, if the set is empty, then this is by default false, because you should take an action from the empty set, which is impossible. So we define that to be false, okay? Likewise for box, we say no matter how you do an action in this set, phi will hold, and that is defined as no matter how you do an A1, phi will hold, and no matter how you do an A2, phi will hold, etc., up to AN. And because if you cannot do anything, this formula holds trivially, we define box empty set phi to be true. Because if you don't do anything, that's also fine with box, right? You agree? Good. And then you could also extend this by allowing kind of algebra on sets, right? So you can have false as the empty set, true as the full set of actions, a single action, complement, union, and intersection, right? So then you can specify complex operations on sets by using these operators, and then use them inside the box, right? So if I want to say you can do anything but A, how do I specify that? You can do any action but A. Oops, sorry. What did I do? Am I still there? So what did you say? Diamond?
Not before that.
Oh, not. Okay. A? This one? Everything but A. Everything but action A. So suppose act is your set of actions. I want to say you can do anything but A. You cannot do an A right now. Well, that's not a good one, right? Let's change the specification. If I want to specify you must do an A right now. You must do an A right now. That's a better word. How do I specify that? You must do an A right now. Several, yeah, maybe.
Complement of set of A.
Complement of, okay, interesting. Complement of A. I need box or diamond. Without a box or diamond, I cannot continue. I need a box or diamond around it.
Okay. A diamond act. And complement of A.
You mean intersection or?
No, the close to them is and.
No. After this, I need a formula. I cannot write any set here. I must do an A. How do I specify? You had a diamond A true. So that says you can do an A, right?
And box A complement of A false.
Okay, that's very good. So this is saying you can do an A right now, and if you do anything but A, you will end up in false. So you'd better not do it that, right? You can do an A, and you cannot do anything else. Right? Note that if we didn't have this construction, we had to write down for each and every action one such formula, which could have been infinite, right? If the set of actions is infinite, then this would have been infinite. Right? Everyone agrees? Let's go on. Right, so the process is deadlocked. You can write that as either this or that, right? So true stands for all actions, right? So it's a set of all actions. Box true false, it means that you cannot, so you could write it like this or write like that. No matter what you do, you will end up in false, so you'd better not do anything. Or you cannot do anything right now. And you could replace this with true, which is the set of all actions, right? And this you can directly type in MCL toolset, right? So you can write down these things with true, false as actions, and then set expressions on actions, right? The process can execute some action, true, true. A must happen, we just wrote it down, right? Right? Phi holds after every step. How do we write that? So phi holds invariably, basically. Any suggestion? Who wants to say first? You had a suggestion, yeah? Box true phi. That holds after every single step. I think we want to hold that to hold after any number of steps. So this is saying that it is possible to do in a step. I don't think that's what is meant. Oh yeah, okay. So this you can interpret in many different ways. This is, according to this interpretation, it says this should hold after every step, and it should be possible to do a step, similar to what you just said, right? Right. But what if I wanted to say that it holds after every number of steps? So not a single step, but it holds invariably after every number of steps. The question is, what if I want to change this description and I ask you phi holds after every number of steps. So 0, 1, 2, 3, 4 steps. How do I specify that?
Box through a star.
Okay, that we haven't seen yet. But let's understand what that means.
Many true.
So we are basically saying after one step it should hold, and after 2 steps it should hold, etc., etc. Maybe if you want 0 steps, you also add this, right? But again, this is not a valid formula, so we need an extension to specify this, right? And the extension I will introduce next is to allow for regular expression, as he just suggested. So you could write not only sets of actions in your formulae, but also regular expressions about action. And a regular expression starts with an empty trace. This is saying you can do nothing, and afterwards phi should hold. Or no matter how you do nothing, oh, there should be a phi here. Phi should hold. And both of them mean that phi should hold right now. Right? So here you are basically writing a trace, or a set of traces. You're saying you should be able to do nothing, and afterwards phi should hold. Or no matter how you do nothing, phi should hold right now. And both of them represent phi. You can say, if you can do beta 1 followed by beta, you should be able to do beta 1 followed by beta 2, and afterwards phi should hold. That is defined to be, you should be able to do beta 1, and then you should be able to do a beta 2, and afterwards phi should hold. Right? And box is just the dual definition. No matter how you do a beta 1 followed by beta 2, phi should hold. This exactly as we also used it here. It stands for 2 juxtaposed boxes. So no matter how you do a beta 1 followed by no matter how you do a beta 2, then phi should hold. Then you can have kind of choice among the traces, right? This is like union of the 2 traces. You should be able to do either beta 1 or beta 2, and afterwards phi should hold. That corresponds to, that is defined to be either you should be able to do beta 1 and then phi holds, or you should be able to do a beta 2 and afterwards phi holds. And box is dual. That's why you get a conjunction here. No matter how you do something of beta 1 or something that corresponds to tracing beta 2, phi should hold. That corresponds to, that is defined to be, no matter how you do beta 1, phi holds, and no matter how you do beta 2, phi holds. Right? And then star, which is a very useful operator, because it allows us to go unboundedly deep in our specification, right? It says, either you do nothing and then phi should hold, or you do beta once and then phi holds, or you do beta 1 twice and then phi holds, etc., etc. So this corresponds to either phi holds now, or you can do a beta 1 and then you have some way of satisfying beta 1 star phi. This is recursive definition, right? It's a very imprecise recursive definition. I will make it more precise later on. But I think it gives you an idea how it works, right? Everyone agrees? Everyone understands what this is supposed to be? Right? And likewise, box is dual. Again, it's a recursive definition, an imprecise one, which says no matter how you do 0 or more times beta 1, phi should hold. So phi should hold right now. And no matter how you do beta 1 once, beta 1 star phi holds. This is typically called the fixed point construction. And this equation may have several solutions. So it's very imprecise, the way of using fixed point. I will make that precise later on. Okay. Any questions? So now getting back to the question I asked before, how do I specify that phi holds everywhere, no matter how many steps I take, phi holds? You said it, so you are not allowed to say it again. Using these constructs, how do I specify that phi holds everywhere in my specification? Box true? Yeah, perfect. So box true star phi says no matter how many steps I take, afterwards phi should hold. Right? Good. Okay, here are some other examples. For example, if I want to generalize the one that the property that I specified before the break. Before the break, I specified that the scientist produces a publication after drinking 2 coffees in a row. If I want to generalize it so that it holds everywhere, then I only need to add a true star before that. So before I had box coffee, diamond pop true, and what was the other one? Box coffee false, I think. Now I can rewrite it using regular expressions. It becomes a little bit more readable. And then I can add in the beginning a true star so that it holds everywhere. Not only now, but everywhere also in the future. Right?
Shouldn't the true be not coffee?
It doesn't matter. So if you put not coffee star, you mean? Yeah. And then you get the same thing. So we don't care if you produce more publications. We only care if you produce too many coffees, right? So if you put not coffee star, if your set of actions is only coffee and tea, then you get the same thing. If you have other actions, then it does matter, right? So if you can, for example, drink a tea, then if you put not coffee here, then after drinking tea, all bets are off. So no one cares what you do next, right? While if you have a true star, even if you drink a tea now and then 2 coffees in a row, you should produce a publication.
But I can now drink 3 coffee, and I would not publish a...
No, you cannot. Because true star stands for that this holds now, and this holds after every single action and every double action, every triple actions, right? But if you replace this with coffee star and you had tea in your sets of actions, after you drink 1 tea, then nothing can be checked. So you are free to do whatever you want, right? You get your salary and then you can just go about drinking as many coffees as you want without producing any publication. Right, so a scientist never drinks beer is true star, beer false. Right, so never beer can if you ever drink a beer, then you should satisfy false. So you'd better not drink beer at all. And invariably phi holds is true star phi. Right? And possibly in the future phi holds. It's either it holds now, or it holds after 1 action or 2 actions, and that you specify by diamond true star phi. Okay? Right. This is a very nice extension. For many practical purposes, this is enough. But still there are some other things that some other types of specifications that you cannot specify using regular expressions. For example, if you want to say all computations inevitably reach a state which satisfy phi. Anyone has an idea how I could have an approximation of this property? So all computations should reach a state in which phi is satisfied. If I want to specify this using regular expressions, how would I get an approximate of this property? Okay, let me erase the board because it's getting a little bit cluttered. So since you want the box true star, I keep the true. Box true star. Diamond true star. Very good. That's a very good approximate of this. However, so what does this say? It says no matter what you do, there is a path always to satisfying phi, right? No matter what you do, there is always a path to satisfying phi. What if I do this? So I have a single initial state. I have a way of spending time on nothing, and let's assume that phi means you can do an A, okay, or you can do a B. So assume that I want to say that, or maybe even better, you should do a B. Okay. So I want to specify that you should eventually be forced to do a B. That's what that says, right? You should be forced to do a B in the future, somewhere in the future. You can never avoid not doing a B, right? what does this say? It says no matter how the system develops, there is always a path to a state in which B is possible, right? Look at this specification. Oops. In this specification, no matter how I evolve, and then you can also have this, just to be sure. No matter how I evolve, either I'm here or I'm there, I always have a path to a state in which B is inevitably possible, right? Namely, if I arrive here, then my only choice is B. And then from all states, this is reachable, so this is satisfied. This formula is satisfied here. Do you agree? No matter where I am, either I'm here or there is always a path to a state in which B cannot be avoided, right? But what can happen in this specification is that I can keep on doing an A and avoid B for an indefinite amount of time, right? So I can potentially avoid doing B by staying in this state. So it does not satisfy the intuitive property. I am saying all computations inevitably reach a state in which phi is satisfied. One possible computation is to do infinitely many A's. And then I'm not forced to do a B. So this is a very good approximate of what I want to specify, but not exactly, because by staying here I can avoid it. Right? So I need another type of machinery to specify this type of a specification. I will introduce that soon. The same holds for this one. For some execution in the future, phi holds everywhere. Again, I cannot specify using the Gödel expression. A very close approximate can be specified, but not exactly what I want. So the way to do this is using fixed points. Right, and fixed point is a standard technique used in many branches of computer science to specify recursive specification and specify which solution are you referring to. I think given the time I will be very brief about fixed points, but I will give you some flavor of. Oh, I don't have the slide for it. I can briefly explain that on the board and then conclude this lecture. I have another set of slides for fixed points, but I don't have time. So if you look at this equation, like n is equal to f of n, for example. Such an equation, depending on f, can have several different solutions. For example, if the equation is n is equal to n squared, how many solutions does it have? Just in normal arithmetic numbers, right? It has two solutions, 0 and 1, right? Both for 0 and 1, this solution is satisfied. If I write n is equal to n plus 0, I have infinitely many solutions for any natural or real or whatever number, and n is a solution to this equation. And if I write n is equal to n plus 1, then there is no solution at all, right? So only for n in the empty set this is satisfied. So an equation can have 0, 1, or many solutions, and thereby you need to specify which solution you're referring to. And you could, for example, say n is the minimal solution to f of n, and thereby I look at the smallest number that satisfies this equation, or the maximal number that satisfies this. And we use the exact same technique to look at solutions to recursive specifications in logic. So when I write x is the minimal solution to x and x or ax, when I say x is the minimal solution to this equation, either x holds right now, or I can do something and afterwards x holds, then I calculate the set of states that satisfy this, and I take the smallest sets that satisfy this formula, and that's the solution I'm referring to. So x is the smallest solution to this equation, the smallest set of states that satisfies this equation. Right? Likewise, when I write x is the maximal solution to x holds right now, and no matter how I do something, x holds in the future, then I calculate the set of states that satisfy this equation, and I refer to the largest one in terms of set inclusion, right? So let's take one or two examples to understand how the calculation of this minimal and maximal fixed point in the simplest setting works. And then if you're interested, in the book there is a whole algorithm about doing this with combinations of minimal and maximal fixed points, etc. And then I'll give you one or two examples of specifications on the spot so that you get a grip of the concept. Okay. So take this specification that we had here, the one that we had a little bit of a problem with. And assume that this state is called S0, and this one is called S1. Okay? And I write this formula. X is the minimal solution to X, or I can do something, and afterwards I can do a B. Or I can do a B, and I cannot do anything but B. Okay? So I'm looking for the minimal fixed point of this equation. And what does this equation say? Either X holds right now, or I can do something no, sorry. Either I should do a B right now, or I can do something, and afterwards I am able to arrive in a state in which X holds. Okay? So either I should do a B right now. That's what this one says, right? You agree with that? B cannot be avoided, basically. B cannot be avoided. I'm changing things on the spot, I'm sorry. So either B cannot be avoided right now, or no matter how I evolve, I will end up in a state in which X is satisfied. Okay? So no matter how I evolve, no matter how I do something, I will end up in X. Okay? Does that make intuitive sense? Even better with this. So either I cannot avoid B right now. No, I think that the one that I wrote before was okay. Either I cannot do a B right, I cannot avoid a B right now, or no matter how I do something, I will end up in a state in which X is satisfied, meaning that eventually B cannot be avoided in the future. Okay? So let's calculate the minimal and maximal fixed point for this one based on this transition system. It's difficult to talk and think at the same time. Jan Friese, do you think this is a good specification? So it's saying either you should be able to do a B and nothing else right now, or no matter what you do, you end up in a state in which X holds again. Meaning that eventually in the future you cannot avoid doing B.
Similar state does satisfy this?
We will do that, but let me make sure that I wrote the formula in a good shape, and then I will do the calculation. We will do the calculation together.
So the meaning of it should be you cannot avoid.
B in the future, no matter how you evolve. No matter what you do, you end up in a state in which B cannot be avoided. box true x, or b cannot be avoided. So no matter how you evolve, you end up in x, or b cannot be avoided right now. I could also turn it into a diamond, true. That says there is a path in which b cannot be avoided, but and then
I'll just think about it. And
that's fine. So let's take this, and then let's start calculating the solutions to this one. How do we do this? Typically, if you have a single fixed point, if you want to calculate the maximal fixed point, you start with the full set, you put it in x, you iterate, and you see whether you get the same x back or not. If you get the same x back, then you have found the maximal fixed point. If you haven't, you start with the second approximation, you put it back in the equation, you repeat once again to see whether you get the same x back or not. You iterate, and then because you have a finite transition system here, you will iterate only finitely many times, and then you will find the maximal fixed point then. Okay? So let's do that. We start with this whole set of states as x. In this case, what is the whole set of states? S0 and S1, right?
well, I think this formula is valid in that one. Is that true?
I don't know, but I've started, so I cannot stop. I should continue calculating. Yeah,
I would doubt whether it's
it's okay. And this shows how tricky fixed point equations can be. Sometimes you can write a formula that is always true or always false. And I've seen many papers, actually, I've seen some papers in which the formulae did not make any sense, right? But, okay, we will come back to this. Now, I want to calculate the maximal fixed point. In which states it holds that either you cannot avoid a b, or no matter what you do, you end up in S0 and S1. Either you cannot avoid a b, which state is that? S1, right? Or no matter what you do, you end up in S0 and S1. No matter what you do, you end up in S0. S0 is does not satisfy this because you can do an A and you stay here, right? If you do an A, you stay in S0. That's okay. If you do a B, you stay in S1. So S0 satisfies this. I'm sorry. Right? No matter what you do, you should end up in S0 and S1. If you're here, if you do an A, you end up in S0, which is okay. If you do a B, you end up in S1, which is also okay. So S0 is in this set. How about S1? S1 is also okay because no matter what you do, you end up in the same set. Right? So I started with S0 and S1, and I ended up with, so either in this or that is S0 and S1. Right? Or becomes union, right? Either in this set or in that set. So I should be either here or there, thereby I get the same set back. Does that make sense to you? Yes?
If we consider the trivial transition system with just one state and a
Self-loop.
transition
Self-loop,
system,
yeah?
I think
With A, for example, or A and B,
A.
yeah? Then it says either you cannot do a B right now, that's empty set, so there is no state that satisfies this part, right? Or no matter what you do, you end up in the set that you started with. If you start with S0, then no matter what you do, you end up in S0, right? So then you get S0 back. So you start with S0, you get S0 back, that's a fixed point, that's the maximal fixed point. So the maximal fixed point to this equation is S0. For this transition system, the maximal fixed point is S0 and S1.
Doesn't this indicate that formula is not correct? For not
I don't know yet. I'm just doing some mathematical calculation. We will get back to this. So if I am interested in this equation with the maximal solution, then in this case I get S0 and S1 back. And in this case I get S0 back. I start with the full set, I get the full set back, right? If I'm interested in the minimal solution, then I start with the empty set. Okay? So let's start with the empty set. Where is the thing? here. Which states satisfy this one in this transition system? Which states satisfy this formula? S1. Which states satisfy no matter what you do, you end up in the empty set? No matter what you do, you end up in the empty set. No state, right? In all these states, you can do something, so no matter what you do, you go out of the empty set, right? So you get empty set back. So empty set union with S1, you get what? S1. So empty set is not a fixed point. You should iterate once again. What is the solution to this one again? S1. What is the solution to no matter what you do, you end up in S1? No matter what you do, you end up in S1. S1. S0 is not a solution, does not satisfy this formula, because you can do an A and you end up in S0, which is not allowed, right? So the only state that satisfies this formula with S1 is S1. S1 union with S1, S1. I've reached the fixed point. So S1 is the fixed point to this minimal fixed point equation. And I think that makes perfect intuitive sense. I have to think a little bit longer because I cannot think and speak at the same time. But it makes perfect sense with minimal fixed point. No matter what you do, you cannot avoid doing B if you're in S1, right? But if you're in S0, you can avoid doing B by staying here, right? So this minimal fixed point equation says, no matter what you do, you can never avoid doing a B in the future, right? So you will eventually end up in a state that B cannot be avoided. And this is exactly what we wanted, because S1 is the only state that satisfies this. S0 does not satisfy it. I'm just talking intuitively. I'm not talking any math here, right? Does that make sense? Maybe, yeah, maybe tomorrow morning I can give you some patterns of a specification using minimal and maximal fixed point, which could be useful. Yeah.
How you are sure that you actually have minimum?
Right. So if you have a single fixed point, typically you have a set of equations. Then the algorithm is a little bit more complex. But you have a single fixed point. You start with a full set, and once you have a fixed point, then you have calculated the maximal one. If you have a minimal, you want to calculate the minimal, you start with the empty set, and once you reach a fixed point, after a few iterations, you have reached the minimal one. If you have a combination of minimal and maximal fixed point, it's slightly more complex. Every now and then you have to reset your calculation, basically.
Just wonder whether there is connections to Tarski fixed point theorem.
There is a lot of connections, yes.
Just want to know the interaction.
Yeah. So basically, if you have a single fixed point, I'm looking at this monotone chain of. This is a monotone function. I'm looking at the chain of sets with the set inclusion property. So if I start with empty set and I iterate, in case of a finite transition system, a finite number of times. In case of an infinite one, countably many times, then I reach.
So you are sure that you.
I do reach a fixed point. If it's finite, then I only need a finite number of steps here. Am I right? Yeah. Good. So I think this is a good point to stop talking about logic. Maybe tomorrow, as I said, I'll give you some patterns so that you don't have to think very hard when you specify formulae. You can use just the patterns that we present. But I think you now have the basic knowledge to use this in your specifications. You can start with Hennessy-Milne logic. Sometimes it's not enough. You use regular expressions. Sometimes regular expressions are not enough. You use minimal and maximal fixed point to go a little bit deeper into the property. And yes?
If you consider the trivial transition system.
Okay, you're interested in trivial transitions. Yeah?
Just S0 and non-transitions.
Okay.
And we compute the minimum fixed point if you include S0 as well.
Yeah, sure. So you start, now, if you want to calculate the minimal fixed point, you start with the empty set.
We start with the empty set, but the first formula is true. And
So you are saying what I wrote down doesn't make intuitive sense. I have to think. I cannot answer this. I will come back to you tomorrow about this, okay?
You are completely right.
You may be right. I cannot say that.
There's a small change to the formula, and then the
But let's get back to this tomorrow because, as I said, I cannot both speak and think. So we'll talk about this tomorrow. Good. So I think we can now move to the example, right? So you had a recipe from Jan Fristo how to go about specifying the interface of the example, the requirements of the example, right? And I think we can spend now 40 minutes or so till 2:45 to get something done with respect to the case study, okay? And we will just go around and check and then talk. Yeah.
Excuse me, can you please brief
Of what you want to do, or
what the machine actually does? I didn't understand it.
would you mind having a look at the specification and then talking to me, because I think some other people may know, and yeah, that's the page. So if you have a look and you have any questions. Okay, fine. Good. Now I understand what you should add here. You should add absence of deadlock. Otherwise, you're right. Absence of deadlock. So you should say true, diamond, true, true, and the rest. Then you exclude this case. But I will get back to you. I will give you a nice pattern to use for tomorrow.